We have been discussing digital to analog converters. At the receiving end, we require a digital to analog converter in order to retrieve the analog data from the digital information which is transmitted from the transmitter side. From the transmitter, even though we are having the analog information, because it is easy for us to transmit and to process the digital information, we are converting analog to digital and then we are sending this data. At the receiving end, again we are converting this digital information to analog information. There we require a digital to analog converter. We have already discussed a digital to analog converter which is binary weighted resistors. Sir, when we discussed already binary weighted resistors, what is the requirement of this another network which we are using for the same purpose, digital to analog conversion? There is no doubt we have discussed binary weighted resistors. That digital to analog converter is very much simple. 2 to the power 0R, 2 to the power 1R, 2 to the power 2R, like that. Binary weighted resistors. If we have 4 bits means 2 to the power 3R, like this. But the disadvantage with the binary weighted resistor method is, when the input digital data at the receiving end is increasing, example we have 10 number of bits, then these resistors weight value is increasing from 2 to the power 0 to 2 to the power 9. We require 10 different resistors. There is no guarantee that all these resistors we will get in the market. If we do not get 1 or 2 resistors, then it is difficult to implement this one. It is simple, and we can use it for the when the input digital data is having very less number of bits. But now the question is, if the input digital data is having more number of bits, then what is the solution? Then we are discussing about R-2R ladder network. Even though you are having n number of input digital bits, this network is capable of converting those n number of digital input information to single analog voltage value. That is the advantage of R-2R ladder network. As the name suggesting, R-2R ladder network, in this network we use only 2 resistors. One is R and the second one is 2R. Even though in the input digital data we have 5 bits or 10 bits or 15 bits, but the number of resistors we are using are only 2. One is R and the second one is 2R. Now I am drawing the circuit. We are taking an operational amplifier in the inverting mode. So I am grounding the non-inverting terminal. I am taking the feedback resistor value as 2R, because I can take any resistors between R and 2R. I am choosing 2R, and I am taking a resistor value R. Then here I am constructing my circuit. This is 2R and this is R. Assume that I am taking 3 bits digital input data. So this is B2, this is B1, and this is B0. Finally I am taking a resistor 2R which I am grounding. Because my digital input is B2, B1, B0, this is most significant bit and this is least significant bit. I am taking 1, 0, 0. Because B2, here I am writing the values, B2, B1, B0, 1, 0, 0. This is MSB and this is LSB. Okay. Now, this is minus VR. When the B2 is 1, we can connect this switch to minus VR. When the B1 is 0, we should connect this to ground. When the B0 is 0, we are connecting this also to the ground. Finally, when we are trying to reduce these resistors, 2R, 2R, these two are in parallel mode. Because 2R, 2R both are in parallel, then the equivalent value is R. R and R both are in series. So the equivalent resistance value is 2R. Now this 2R and this 2R both are in parallel. Because both sides, this side the potential is same, this side the potential is same. Both are in parallel configuration. So the equivalent resistance value is R. Now R and R both are in series. So the equivalent resistance value is 2R. Now we cannot reduce this. These two are not parallel. Here the potential is same, but here the potential is not same. Here the potential is 0, here the potential is minus VR. I can use the Thevenin's theorem to reduce the resistance here. In order to use the Thevenin's theorem, first we have to recollect what is the Thevenin's theorem. In the Thevenin's theorem, if this is a voltage source V and we are using a resistor R1 and this is R2 and this is R3. Now we can reduce these two resistors to one resistor by using the Thevenin's theorem. For that I am using R Thevenin, V Thevenin and R3. What is the value of this R Thevenin? In order to get the R Thevenin value, we should short the voltage source. When voltage source is shorted, R1 and R2 both are in parallel configuration. So the R Thevenin value is equal to R1 into R2 by R1 plus R2. V Thevenin value is equal to V into R2 by R1 plus R2. By using this, we are trying to reduce this one. Now I am drawing this circuit similar to the circuit we have already drawn here. Here minus VR is there. We have drawn like this. Okay. So it is nothing but minus VR, 2R, 2R. This is how we are connecting. There is no need to confuse. Here I have drawn two resistors R1 and R2. From this we can take the Thevenin's equivalent resistance value and Thevenin's equivalent voltage value. In order to take the Thevenin's equivalent resistance value, voltage source should be made as 0. When we are shorting this one, then the equivalent resistance value R Thevenin is equal to R, because both resistors are in parallel configuration. The V Thevenin value is equal to reference value minus VR into R1 into R2, because both values are 2R only. So this is minus VR into R2, minus VR into R2 by 2R plus 2R. This is equal to minus VR into 2R by 4R. So this is equal to minus VR by 2. So this I can reduce as simply a resistor value R, because R Thevenin value is equal to R, and a voltage source value minus VR by 2. So finally I am bringing this to here. This is R and this is minus VR by 2. Now R and R both are in series. Because both are in series, the value is 2R. This is minus VR by 2. This is operational amplifier working in inverting mode. Because the operational amplifier is working in inverting mode, the gain of this is V0 is equal to minus RF by R1 into Vin. Therefore, RF minus RF is equal to 2R, R1 is equal to 2R, Vin is equal to minus VR by 2. Finally, the value is VR by 2. So, when we give the digital input 100, when we are giving the digital input 100, equivalent value here we are getting VR by 2, the equivalent analog value. Analog value we are getting VR by 2. This is how we can convert the digital input to analog value. And now, even when we want to get 0, 1, 0, you can do the assignment for 0, 1, 0 or 0, 0, 1. Even we can do the same procedure for 4 bits or 5 bits or 6 bits or for n number of bits. Even though we are having n number of the digital inputs, we are using the same resistor combinations R and 2R. If we are having 4 bits means one more wing of R-2R ladder network will increase. This is how we can convert the digital to analog by using the R-2R ladder network.